Hi, this is Karina Slater reporting on the Falling Object Lab for Physics 2211, Section M5. The main objective of this lab was to model a slow-falling object and a fast-falling object in Python based on videos recorded of both being dropped from rest. The main result was that the net force equals the force of gravity plus the force of drag model was an accurate model for the two falling objects. The drag for each had to be different, though, as the slow-falling object had more drag than the fast-falling object. Here is the first frame of the paper video. I started the video while the paper was at rest in my friend's hand. You can see the initial conditions, including initial position, mass, frame rate, length of clip, and calibration length, in the bottom right corner. You can see I have marked the axes, object, and calibration stick in the video. The axes are oriented so that the object falls down the negative y-axis. Here's the middle of the clip. You can see the blue dots tracking the motion of the object. And here is the end of the video. I stopped the video right before the object hits the ground. This is the first frame of the aluminum video. Again, I started the video while the aluminum was at rest, right before it was dropped. The initial conditions are again in the bottom right corner of the frame, and I have marked the axes, object, and calibration stick. The axes are again oriented so that the object falls down the negative y-axis. Here is the middle of the clip. You can see the red dots tracking the motion of the object, just as in the paper video. And here's the end. I stopped the video right before the object hits the ground. This is the code I used to model the objects falling from rest, affected only by the force of gravity in this case. In the top right corner, I have listed the initial conditions for both my paper and aluminum model. These conditions include initial position, mass, initial velocity, time step, and run length. I chose the time step so that it was small compared to the total run length. On the right side of the page, near the bottom, I have listed Newton's second law, delta P equals F net delta T, from which I derived the velocity update and position updates you can see below the law in the bottom right-hand corner. My net force is only based on gravity for this model. In the diagram you can see I've made the force be in the downward y direction since the force of gravity points toward the Earth, which is down the y-axis in this case. I have also labeled the motion of the object as P in the diagram. Here's the code I used to make the model that included drag in the net force. Again, my initial conditions are listed in the boxes in the top right corner. The only change in the code is that I have added the force of drag. The force is proportional to the velocity of the object times the constant b. I found b for each object by experimenting with the value to find the one that outputted y positions that matched with the y positions taken from my recorded video at the same times. I obtained 0.015 kilograms per second for paper and 0.005 kilograms per second for aluminum. The value for B for the paper was larger than the value of B for the aluminum. This makes sense because the paper took longer to reach the ground, meaning it had more drag than the aluminum. In the diagram, you can see that the drag force is oriented upward along the y-axis because it is opposite the motion of the object. Here is the graph of the outputted data from both models and the video for the paper. As you can see, the model with drag, while not a perfect fit, is a good fit for the data taken from the video. One reason the model may not be a perfect fit is that the paper did not fall completely in a straight line. It twisted and veered to the left a little bit. However, since it is a good fit, we can conclude that the F net equals the force of gravity plus the force of drag is an accurate model for the falling paper. Here's the data for the aluminum. The model with drag and the model without drag are very similar, which makes sense because the aluminum ball is a heavier object, so it falls further before it is affected by drag. However, you can see that the model with drag is a better fit for the data taken from my video. Its endpoints end up in the same position as the endpoints for the video data. Thus, the net force equals the force of gravity plus the force of drag is an accurate model for the falling aluminum. So what does this mean? Which model resulted in terminal velocity? The answer is the model with drag. Terminal velocity is when gravity and drag cancel out and the velocity of the object becomes constant. When I formatted the model for paper to output a velocity versus time graph over a long time period, only the model with drag resulted in a constant velocity. What if the paper was thrown with an initial velocity down the y-axis? Would the models result in a terminal velocity? I used the same drag and no drag models I just used to output a velocity time graph over a long period of time, except I added a velocity in the negative y direction. Just as I explained before, only the model with drag resulted in a terminal velocity.